We will now see how to solve these equations using our first method, which is called as the matrix inversion method. So we call it as the matrix inversion method, and we will go through the steps involved in using this method to solve the set of linear equations. So we had our matrix equation as Ax equal to B, so where A is the coefficient matrix of the set of variables which has the coefficients of all the variables in all the equations. X is a vector containing the variables, which is what we want to solve and find out, and B is a set of numbers on the right side of the equations. So we are interested in solving for X and finding the value of the vector X. Now normally if we had this as a set of numbers, we would simply write this as X equal to B divided by A. But now, because these are matrices and vectors, we can't simply do that. So what we do is we multiply this with another matrix called A inverse. So we multiply both sides of the equation with another matrix called A inverse. So A inverse into A into X is equal to A inverse B. Now A inverse is nothing but the inverse matrix of the matrix A. So it's like if I give you a number 4, the inverse of 4 is 4 inverse is 1 by 4. And when you multiply 4 with 4 inverse, so 4 into 4 inverse will give you 1, right? Similarly, if I have any number A and we multiply it with A inverse, or we multiply A inverse with the number A, we would get 1. It's like 1 by A into A, 1 by 4 into 4. It's equal to 1, right? Similarly, in matrix notation, A inverse is the inverse of matrix A, where when we multiply the inverse of a matrix with the matrix itself, it gives us the matrix equivalent of 1, which is called as the identity matrix. So A inverse into A is equal to I, which we call as the identity matrix, right? It's like the number 1. So the identity matrix has the form of, so the identity matrix, it has 1 on the diagonal and zeros everywhere. So all the other numbers would be 0. Because our A matrix is 3 by 3, that means our A matrix had 3 rows and 3 columns. The identity matrix would also be 3 by 3. If it is 2 by 2, then we'll have only this part. So the identity matrix is a square matrix. That means the number of rows and columns would be the same. If it has 3 rows, it will have 3 columns. If it has 4 rows, it will have 4 columns. If it's 5 rows, 5 columns, and so on. So the number of rows and columns in the identity matrix would be the same. And the identity matrix would have a value of 1 on all the diagonal positions. So the diagonal elements would be 1, and the off-diagonal elements of the entire matrix would be equal to 0, as we see here. So the diagonal elements are 1. All the off-diagonal elements would be 0. For whatever the size of the identity matrix is. So it's the matrix equivalent of the number 1 in the normal numbers that we are used to. So when you multiply 1 with any number or with any variable, you get back the same. 1 into 5 is 5. 1 into x is x. 1 into b is b. 1 into z is z. 1 into 100 is 100, right? So A inverse into A becomes the identity matrix, which is the matrix equivalent of the number 1. So this product here, A inverse into A, is I, and I into X, because I is like the number 1, I into X in matrix terms would give you X. So we will have this equation as, so therefore it becomes A inverse A X equals A inverse B, which is I X equals A inverse B, and that would imply x equals A inverse B. So I into x, I is like the number 1 in matrix terms, so the I into x is x, and therefore we have our solution would be to solve for x. So x equals A inverse B. So all we need to do is to find the vector x which contains the variables small x, small y, and small z. We need to find the inverse matrix A inverse and multiply it with the B vector. So we have the vector of numbers which is called as the vector B, which is the right side of our equations. So in this case it's 5, 0, 5, and we have to multiply that vector with the inverse of the coefficient matrix, and that would give us the solution for the variables x, y, and z, which we denote as a vector capital X. So how do we find the inverse of a matrix? So we had a matrix as we have seen earlier, which was represented by 1, minus 1, 3, and so on. How do we find, or what are the steps involved in finding the inverse of the matrix? Now the inverse of the matrix is given as, or we denote it as A superscript minus 1, so that's A inverse. It is defined as what we call as the adjoint matrix of A divided by the determinant of A. So determinant of A, of the coefficient matrix, that is. So the inverse of the matrix A, of any matrix A, is given by the adjoint of the matrix A divided by the determinant value of that matrix. And clearly, if you remember, we said that a solution exists only if the coefficient matrix has a determinant that is not equal to 0. And that becomes obvious from this representation here, where if we had this denominator, the determinant equal to 0, that means we are going to divide some matrix by 0. So division by 0 will give us infinity, right? So having the determinant value as 0, that means the inverse matrix does not exist. If the inverse does not exist, we can't solve for this equation, because to solve for the x vector or for the variables, we need to have the inverse matrix, which we will multiply with the vector B to get our solution. But if the determinant is 0, the inverse does not exist, and therefore we won't have a solution for those set of equations. So that's something that becomes obvious as soon as we have this equation for the inverse matrix, which makes it clear as to why a matrix which is singular cannot give us a solution. Now, what do we mean by the adjoint matrix of A? The adjoint matrix of A, so we need to define that. And adjoint of A, adjoint of a matrix A, we will write it in short form as ADJ in brackets A, adjoint of A. It is nothing but the transpose of the cofactor matrix. So we'll define what is called as C transpose. And the matrix C is called as the cofactor matrix, where C is the cofactor matrix. So we can define the inverse of a matrix A as the transpose of the cofactor matrix divided by the determinant of the matrix A. So we can equivalently write this definition for A inverse as C transpose, which is nothing but the adjoint of A divided by the determinant of A. So that's our inverse matrix. And someone asked me in the previous lecture, why are we computing the transpose, or what is the purpose of finding the transpose? And here it is. The purpose of finding the transpose, or knowing what is a transpose, is because we are interested in finding the inverse of the matrix, and for the inverse we need to find the transpose of the cofactor matrix. So interchanging the rows into columns and columns into rows gives us the transpose of a matrix. So we'll first find what is called as the cofactor matrix, which we denote by the letter capital C, and then take its transpose. That would give us the adjoint matrix of A, and then divide the adjoint matrix of A divided by the determinant value of A. That would lead us to, or give us, the inverse matrix of A. And using that inverse matrix, we will solve for the variables which are represented in vector form by the letter capital X. Now what we will see next is to find the cofactor matrix C, or the procedure to find the cofactor matrix C from the given matrix A, and then we know how to compute the transpose, and then from the transpose we can eventually find the inverse, because we have already found the determinant value of this given set of equations, and we got that determinant as equal to 40, which is not equal to 0. So what we will do is first see how to compute or determine the cofactor matrix C. From our set of equations, we have our coefficient matrix A given by this matrix 1, minus 1, 3, 4, 2, minus 1, and 1, 3, 1 as the three rows of the coefficient matrix. Excuse me. And we are now interested in finding the cofactor matrix C. The cofactor matrix is nothing but a matrix where each of these elements of A has been replaced by its respective cofactor. So the number 1 here, the element 1 here, has a cofactor which is given by these numbers, this submatrix, which is when we close the row and column where that 1 is present, we get this submatrix here, which we cross multiply and find the cofactor. So that is nothing but the cofactor of 1. And similarly for the cofactor of minus 1, it would be 4 minus 1, 1, 1, of course with the positional sign for that location, for that position, right? So we'll have to find the cofactor of each of these elements of A, and then replace those elements with their respective cofactors. That would give us the cofactor matrix. So we have to compute the cofactor of each of these numbers one by one. So let's do that very quickly. The cofactor of the first element, which is 1, cofactor of 1, is equal to, we have to close the row and column and write down only the numbers which are left out. So 2 minus 1, 3, 1. So that's that's the cofactor of 1. And of course, because we have the positional sign sets, that's plus, minus, plus, minus, plus, minus, plus, minus, plus. So we should not forget the positional sign when we are writing the cofactors. For the first element 1, the positional sign is plus, so we'll write that plus here and compute the cofactor, which is nothing but 2 minus, that's 2 into 1 is 2, minus 3 into minus 1 is minus 3, so we get that as 5. Similarly, we'll find the cofactor of the next element, which is minus 1. So that's equal to, so we'll have to close the row and the column where that minus 1 is present. So that leaves us with 4 minus 1, 1, 1. So we'll write that 4 minus 1, 1, 1. And the positional sign on that minus 1 is minus. So we put that minus. And that would give us the cofactor of minus 1, which is a minus of 4 minus minus 1. So it will be minus 5. So the cofactor of minus 1 is minus 5. Similarly, the cofactor of the next number 3 is, we close the row and the column. So we are left with these 4 numbers. And the positional sign here is plus. So we'll put that plus also in front. So it will be plus. And the cofactor is 4, 2, 1, 3. So that gives us 12 minus 2. So 12, 4 3s are 12 minus 2, which is equal to 10. So you get 10 as the cofactor for 3. Similarly, we'll do it for the second row now. Cofactor of 4 is equal to, so we'll have to close the row and column. So the row is here where the 4 is present, and the column is here where the 4 is present. So we close this column and this row. We are left with these 4 numbers: -1, 3, 3, 1. So we'll have it as -1, 3, 3, 1, and we find the determinant of it. And of course we should not forget the positional sign, which is minus here, so we put that minus in front. So that will give us -1 into 1 is -1. We are cross multiplying now. Minus 3 into 3 is 9. So minus of -10 will become 10. So we have the cofactor of 4 is also equal to 10. Similarly, the cofactor of 2 is equal to, the positional sign is plus. We'll close the row and column where the 2 is present. So we close this row and this column. So we are left with 1, 3, 1, 1. So 1, 3, 1, 1. And that gives us 1 minus 3, which is equal to -2. So that's the cofactor of 2, which is equal to -2. And then we'll find the cofactor of the next element, which is this -1 here. So I'll have to move on to the next page. So the cofactor of -1, cofactor of -1 will be equal to, the positional sign is minus, and when you close the row and the column, you will have 1, -1, and 1, 3. So the cofactor of -1 will be minus of 1 into 3 is 3 minus -1. So that will be equal to 3 plus 1, 4. Minus of 4 is -4. So the cofactor of the -1 is -4. So now we move on to the third row. So the cofactor of the first element in the third row, the first element is 1, and it has a positional sign of plus. And if you close the row and the column, or the numbers that are visible are -1, 3, and 2, -1, 2, -1. So now we compute that, we get -1 into -1 is 1, minus 2 into 3 is 6. That gives us -5. So the cofactor of the first element in the third row, which is 1, is equal to -5. Similarly, the cofactor of the second element in the third row, the second element in the third row is 3, and the cofactor would be, the minus is the positional sign, and we'll need to close the row and the column and find the remaining numbers, which would be 1, 4, 3, -1. And that would be minus of 1 into -1 is -1, minus 12. So minus of -13 would make it as +13. So we'll have the cofactor of 3 as 13. And finally, the cofactor of the last number, or the last element in the last row, which is 1, is equal to, the positional sign is plus. When you close the row and column where that 1 is present, you are left out with the 1, -1, 4, and 2. So that gives us 1 into 2 is 2, minus -4. So that's equal to 2 plus 4, which is 6. So we have now computed the cofactor of each element of the matrix A. So with these numbers, we can now write our cofactor matrix. So the cofactor matrix can be written as, so cofactor matrix of A is C equal to, so in the place of each of the numbers of A, we will write their respective cofactors. So we will have it as 5 minus 5, 10. So the first row elements had the cofactors 5 minus 5 and 10. Similarly, the second row elements had their cofactors as 10 minus 2, and minus 4. And the third row elements had their cofactors as minus 5, 13, and 6. So that's our cofactor matrix. So to find the cofactor matrix, we find the cofactor of each element of the matrix A and then replace that element by its respective cofactor. Next, we can find the adjoint of A. So the adjoint matrix of A, is, we simply write as adjoint of A is equal to the transpose of C transpose. So that means we have the cofactor matrix here. We need to interchange the rows and columns. So the first row, 5 minus 5, 10, we'll write it as a column. So that would give us 5 minus 5, 10. We are interchanging the rows into columns. Similarly, the second row becomes the second column, which will be 10 minus 2 minus 4. And the third row becomes the third column, which is minus 5, 13, and 6. So that's our adjoint matrix of A. So you see that the rows have been changed into columns and the columns have become rows. So the row here, 5 minus 5, 10, has become a column, 5 minus 5, 10. Similarly, the column here, 5, 10, minus 5, has become a row here, 5, 10, minus 5. So the rows and columns have been interchanged, and that gives us the transpose of the matrix A. Now, from the transpose of the matrix C, that is. So from the transpose of the cofactor matrix, we have got, that is the definition for the adjoint matrix, and from that we can now find the inverse matrix. So the inverse of A, which is A inverse, is equal to the adjoint of A divided by the determinant of A. So which is nothing but the adjoint of A is this matrix here that we have here, and we have to simply divide it by the determinant of A, which we earlier found out to be equal to 40. So previously we computed that value to be 40. So we have to divide this matrix by a constant 40, and when you divide a matrix by a constant factor, it means we are dividing each element of this matrix by the same number. So dividing by 40 here means 5 by 40, 10 by 40, minus 5 by 40, minus 5 by 40, minus 2 by 40, 13 by 40, 10 by 40, minus 4 by 40, and 6 by 40. So we will just keep that 40 outside the matrix for now. So we'll simply write that as 1 by 40 because we are dividing by 40. And the C matrix or the C transpose, we will keep it as it is. So 5, 10, minus 5, minus 5, minus 2, 13, and 10, minus 4, and 6. So that's our, let me write that properly. So that's our inverse matrix of A. Now when we multiply the matrix A with its inverse, it should give us the identity matrix, and I would leave that as an exercise for you to compute the to check whether multiplying A inverse with A indeed gives you the identity matrix of 3 by 3, where the diagonal elements are 1 and all the others are zeros. Now we can use this inverse matrix to find our solution for the vector x. So our solution is x equals A inverse B. So A inverse, we got it as 1 by 40 into 5 10 minus 5 minus 5 minus 2 and 13, 10 minus 4 and 6. So that's our inverse matrix. So let me just check if I've written the correct numbers. So 5, 10 minus 5 minus 5 minus 2, 13, 10 minus 4, 6. Okay, so we have our inverse matrix there, and we have to multiply that to the vector b, which is 5 0 5, which is what is we obtained this from the question, the equations that were given to us, which we are trying to solve. Now multiplying this would give us the solution for our set of equations. So what we'll do now is we'll first multiply this. We'll first multiply this matrix. We'll keep the 1 by 40 outside. We'll first multiply this matrix with this vector, and then finally in the last step we will take the 1 by 40 into the matrix. And when you're multiplying matrices and vectors, or two different matrices, one of the conditions you have to make sure is that the matrix dimensions are matching. So what do we mean by that? The matrix dimensions should be such that the number of columns and the number of rows in the other matrix, the number of columns in the first matrix and the number of rows in the other matrix should be the same. So we have 1 2 3 columns, 1 2 3 rows. So the number of columns and the number of rows should match. We call this as the inner dimensions of the matrix should match. Otherwise the matrix multiplication operation, or the multiplication of a matrix with a vector, is not possible. So we verified here already that the number of columns and the number of rows in these two matrices are same. So we have 3 columns and 3 rows here, so we can proceed with our multiplication of these two matrices, or with this, between this matrix and this vector. So we'll keep the 1 by 40 outside still, and we will just multiply it row by row. So 5 into 5 plus 10 into 0 plus minus 5 into 5. So 5 into 5 is 25, plus 10 into 0 is 0, plus minus 5 into 5 is minus 25. So plus minus 25 is minus 25. So that's the first element we get here. Then we multiply the second row with this entire column, element by element, and add them together. So minus 5 into 5 is minus 25. Minus 2 into 0 is 0, so it's plus 0. And 13 into 5 is 65, so plus 65. So we get this number. And then we multiply the third row with this column 505. So 10 into 5 is 50, plus minus 4 into 0 is 0, so that's plus 0, plus 6 into 5 is 30, so that's plus 30. So we now have this as 1 by 40 into, so 25 plus 0 minus 25, that's 0, and 65 minus 25 will be 40, and 50 plus 30 is 80. So we have this for the value x. Now we can take this 1 by 40 inside the vector, so that is equal to 0 by 40, 40 by 40, and 80 divided by 40. So that's our vector of solutions that we're getting. So that's 0 by 40 is 0, 40 by 40 is 1, and 80 by 40 is 2. So the vector x is equal to 0 1 2. So capital X, the vector x, is nothing but it contains the elements small x, small y, and small z, which is equal to 0 1 2. So that means our solution is x equal to 0, y equal to 1, and z equal to 2. So that's the solution, or the values of x, y, and z that would satisfy all the three equations. So what we have seen here is not the procedure that we have done is the method of solving a set of linear equations by what is called as the matrix inversion method, because we solve this by finding the inverse of the matrix of the coefficient matrix. So we call this as the matrix inversion method. So we compute the inverse of the coefficient matrix and then multiply that inverse matrix with the constant vector, the b vector, and that gives us our solution. So this method that we have seen is called as the matrix inversion method to solve a set of linear equations.